So we're going to use the chain rule here, and we're going to write it as y equals what? How are we going to break this up into a composition of two functions?
U to the 1/3.
U to the 1/3 is a good start, and that will make u equal to what?
5x squared minus x plus 4.
5x squared minus x plus 4. All right. So what's dy du? Dy du should be, how do we take the derivative of u to the 1/3? Should be
1/3 times u to the negative 2/3.
1/3 times u to the negative 2/3. And I'm going to try to stop writing u to the negative 2/3. I'm just going to write the u in there, if everyone's okay with that. And then times the derivative of u, which is 10x minus 1, which gives us a derivative, if we rewrite this in a nicer form, of 10x minus 1 over 3 times 5x squared minus x plus 4 to the positive 2/3. Everyone good with that?
Makes sense.
Excellent. Any issues with that? Everybody good? Should we do the next one?
Yep.
All right. So y equals 2z plus 5 to the 3rd times 3z minus 1 to the 4th. How are we going to do this?
Both the product rule and the chain rule.
That's right, product rule, and then the chain rule within it. So using the product rule, we'll call this one u, and we'll call this one v. And so as we find that derivative, y prime should be u times the derivative of v. So what does v equal? V equals, we'll call it, we'll need some other variable here, right? Something to the 4th power. What variable do you guys want to use? We're going to use the chain rule on the derivative of 3z minus 1 to the 4th. Nobody has a variable they want to use it. Q, all right, Q to the 4th with Q equal to 3z minus 1. So how are we going to take the derivative of that?
I did it in the morning. 7:44.
Derivative of v equals q to the 4th should be what?
Oh, 4 times 3z minus 1 to the 3rd.
Yep. And then the derivative of this q, 3z minus 1, should be 3. And then what? Plus on the other side, we'll have 3z minus 1 to the 4th. And how are we going to take the derivative of u? U is equal to, what's a variable we want to use for that?
A.
A, all right, a to the 3rd with a equal to 2z plus 5. So what do we get? We get 3a squared. So that'll be 3 times 2z plus 5 squared times what?
2.
2. All right. Everybody good with that as your derivative to start with?
How did you get the 3 in the 4 times 3z minus 1 cubed times 3?
Right, so we were taking the derivative of v, taking the derivative of 3z minus 1 to the 4th. So we wrote that as v equals q to the 4th because we need some variable, right? Q to the 4th with q equal to 3z minus 1. So the chain rule says derivative of v for q cubed, and then times derivative of q, derivative of 3z minus 1 is 3. So that's where that 3 comes from.
All right.
Good?
Yep.
Okay. Anybody else questions on that? All right, so that answer is an okay answer, but what if I asked you, when does this have horizontal tangent lines? You'd have to know when this equals 0, right? Which would probably be a little bit of a problem. So let's see if we can simplify this down. I just want to make sure you guys know how to simplify something like this down to factor it fully. So let's think about the constants. Like this is one term, right? And this is the other term. So let's see, what's the constant that this first one has? A total of 12, right? 4 times 3. And this one has a constant of 3 times 2, which is 6, right? So what can we factor out of that?
6.
6, okay. And then let's see, what else? This has a 2z plus 5 to the third, and this has a 2z plus 5 to the second. So what can I take out? 2z plus 5 to the second. And if this one has 3z minus 1 cubed, and this has 3z minus 1 to the fourth, what can I factor out of that?
3z minus 1 cubed.
Yep. And then what's left? 2z plus 5 cubed gives us what? If we took out the 2z plus 5 squared, it just gives us a 2z plus 5. And if we took a 6 out of the 4 times the 3, what's left? Just a 2, right? Everybody good with that?
Yes.
Okay. And then what's left over here? We took out 3z minus 1 cubed from the 3z minus 1 to the fourth. So that leaves us with 3z minus 1. And then we took out the 3 times the 2. We took out the 6, and we took out the 2z plus 5 squared. So all that's left on the right-hand side is just the 3z minus 1. And what is left inside those brackets there? 2 times the 2z is 4z, plus the 3z is 7z, and plus 10 minus 1 is plus 9. Everybody good with that? So if I asked you, when does this equal 0, you'd get 3 answers, right? What are those 3 answers? Should get negative 5 halves from the first one. You should get positive 1/3 and negative 9/7. Everybody good with that or no?
We're good.
All right, just making sure. Everybody thinks they could simplify that on their own if they needed to in the future? Hopefully so. All right, why don't you guys see if you can find this derivative on your own. Take like 2-3 minutes and find this derivative. This is 3x plus 1 to the 6th power, not a 6th root. So to the 6th power, not a 6th root. Take a minute or two, see if you can figure that derivative out. You guys finished with that or still working on it?
Still working.
All right. How we doing? We good, or you guys still need another second here? Done or no?
Done.
Oh,
All
done.
right. All right, let's start going through it. So 3x plus 1 to the 6th times root 2x minus 5 is a product rule. So 3x plus 1 to the 6th. And then the derivative of root 2x minus 5, we call that root u, with u equal to 2x minus 5. So the derivative of root u is 1 over 2 root u times the derivative of u, and then plus the root 2x minus 5 times the derivative of 3x plus 1 to the 6th, and 3x plus 1 to the 6th, we'll call that v to the 6th, with a v equal to 3x plus 1. So that should be 6 times 3x plus 1 to the 5th times the 3 of the 3x plus 1. Everybody good with that?
Yep.
Okay, cancel out those 2's. So should we simplify this down or no?
Sure.
All right, so how can we do that? We need to get a common denominator. So we'll multiply by root 2x minus 5 over root 2x minus 5. So I can just square that root 2x minus 5 in the numerator. And so that'll give us a root 2x minus 5 as our full denominator. And then up in the top, what can we factor out? We've got a 3x plus 1 to the 6th and a 3x plus 1 to the 5th. So we can take out the 3x plus 1 to the 5th. And then what do we have here? We have 3x plus 1. And then plus, on this side, we've got 18 left. And the root 2x minus 5 times root 2x minus 5 is just 2x minus 5. And we should be able to simplify that out to 3x plus 1 to the 5th. And then what's the other one in the numerator there? That's 36x plus 3x is 39x. And then minus 90 plus 1 is minus 89 over root 2x minus 5. Everybody good or no?
Yeah, that makes sense.
All right.
Is it better to do square root u rather than u to the 1/2?
Oh, it doesn't matter. I mean, you could write it either way. 1/2. If you write it as u to the 1/2 and you do 1/2 u to the negative 1/2, it's going to look the same. I prefer to do the root u to the 1/2 root u just because I like to leave things inside that square root if I can. But it doesn't matter.
Kind of an odd question, but is there a reason that you had to put the square root of 2x minus 5 as like a common denominator? Like, wouldn't it have been fine just under one of them?
Yep, it would be fine. But suppose and I just wanted to like make sure we can all do this, because if I ask you, all right, when does this have horizontal tangent lines? You need to know when the derivative is equal to 0. And in the form that we had it with just this over root 2x minus 5 plus this other thing, that's really hard to figure out. But if we simplify it to this, we can really easily see that it equals 0 when x is negative 1/3 and when x is 89 over 39 by setting the two pieces of the numerator equal to 0.
Okay, thank you.
No problem. Everybody good? All right, what about this one? What's going on with this one?
They're kind of like there's 3 composite functions instead of the usual 2.
Yeah, so it's got a composition within a composition, right? And so if we're going to deal with that, let's take the outermost composition. So the simplest thing that we've got going on here is some function to the 3rd power, right? And what is the u value for going to the 3rd power?
Tangent of 4.
Yeah, should be u equals tangent of 4x. Okay, so the derivative of y equals u cubed should be what? Just 3u squared. But what about the derivative of the u equals tangent 4x? In order to do that, what we really got is u equals tangent of, let's say, v, with v equal to 4x. Everybody see that? So we're going to use the chain rule within the chain rule there. Everybody good with that or no?
Yes, we're good.
What's that? Yeah?
We're good.
You're good. Okay. Derivative of tangent v should be secant squared v, and the derivative of v should be 4. So we end up with 12u squared, which is tangent squared 4x, and then secant squared v, which is secant squared 4x. Okay. So the chain rule within the chain rule, try to take the outermost function and write it as your first composition, then you'll have to do a second composition with your u. You guys see that? Everybody good with that?
I have a question.
Yeah.
Can you go directly from tangent 4x into secant squared 4x?
Well, you have to know because it's 4 secant squared 4x.
Okay.
Because of the chain rule, because it's 4x in there, not just an x in there. If it was just an x, tangent x, then it'd be secant squared x. But because it's tangent 4x, you have to use the chain rule on it. It's the tangent of a function,
Okay.
rather than just the tangent of a single variable. Good?
Yes.
Cool. All right, let's do another one. In fact, why don't you guys do this one on your own? This one only requires one use of the chain rule. So figure out for me the slope of the line tangent to sine to the fifth x at x equals pi over 3. What was your derivative? You did y equals u to the fifth, hopefully, with u equal to sine x, which gave you 5u to the fourth times the derivative of u. Anybody not get that as their derivative? Okay, and then where are we going to evaluate that at x equals pi over 3? So that's just 5 times sine of pi over 3. What's the sine of pi over 3?
Root 3 over 2.
Root 3 over 2 to the fourth, and then cosine of pi over 3, which is 1/2.
1/2.
All right, so we're going to end up with what in our denominator? 2 to the fourth times 2, so 2 to the fifth, which is 32. And then root 3 to the fourth should be what?
9.
Right, times the 5 gives us 45. Good or no?
That makes sense.
All right, cool. All right, let's do this one together. We're going to find the horizontal tangent lines of y equals cosine 2x plus 2 cosine x. I want to make sure you guys know how to solve these trig equations when we get there. So if we're talking about a horizontal tangent line, what does that tell you?
Slope equals 0.
That our slope, y prime, needs to equal 0. Our derivative needs to equal 0, right? Because it's a horizontal tangent line. And so what do we first need to do? We need to find the derivative. What's the derivative of cosine 2x? And hopefully you'll start to get to the point where these ones that are pretty simple, like cosine 2x, you can do in your head with the chain rule rather than writing it all out, but we'll write it out. We got y equals cosine u with u equal to 2x. So what does that give us? Negative sine u, and then times the derivative of u, so negative 2 sine 2x. And then what about the 2 cosine x? Just becomes what?
Negative 2 sine x.
Minus 2 sine x. Everybody good there? All right, what do we need to do with that? We need to set it equal to 0. And what can we divide everything by?
Negative 2.
Negative 2. So we got sine 2x plus sine x equals 0. And how do we solve that trig equation?
double angle identities?
Exactly. Turn sine 2x into 2 sine x cosine x plus the sine x equals 0. And now they both have a sign in the left-hand side, so we'll factor out the sign. To get that. And we've got sine x equals 0, or 2 cosine x plus 1 equals 0, which is x equals what? For sine x equals 0, x is either 0 or pi. And what about this? This tells us that cosine x equals negative 1/2. And when is cosine equal to negative 1/2?
Okay, there's
What's that? You should all be able to tell me like immediately, when does cosine equal negative 1/2? First off, which quadrants does cosine equal negative 1/2 in?
2 and 3, so 2 pi over 3, 4 pi over 3.
2 pi over 3 and 4 pi over 3. You should all be able to tell me that right off the bat. Okay, you need to know the values of cosine and sine and tangent for 0, pi over 6, pi over 4, pi over 3, pi over 2, right? 2 pi over 3, 3 pi over 4, 5 pi over 6, pi, and so on, all the way around that unit circle. You should know the values of sine, cosine, and tangent for all of those angles. So have we answered the question here?
No.
No. What's the question asking us? What are the horizontal tangent lines? So horizontal lines have an equation of y equals something, right? So we need to figure out what happens if we plug in 0 for y of 0. So what is that? That's cosine of 0, which is 1 plus 2 times the cosine of 0, which is also 1. So 1 plus 2 gives you 3. So y equals 3 is 1. What about the next one at pi? Y of pi is equal to what? Cosine of 2 pi is still 1. And then the cosine of pi is negative 1. So this is 1 minus 2 or negative 1. Y equals negative 1 for the second one. And then what about the other ones? Y of 2 pi over 3. Cosine of 4 pi over 3 is what?
Negative 1/2.
Negative 1/2. And then 2 times the cosine of 2 pi over 3. So plus 2 times negative 1/2, which gives us negative 3/2. And what about y of 4 pi over 3? Cosine of 2 times 4 pi over 3 is the cosine of 8 pi over 3. And what's the cosine of 8 pi over 3?
Positive
still
1/2.
negative 1/2.
Still negative, because 8 pi over 3, if we subtract 2 pi from that, gives us 2 pi over 3. So 8 pi over 3 is the same angle as 2 pi over 3 effectively. So the cosine of 2 pi over 3 is negative 1/2. And then plus 2 times the cosine of 4 pi over 3, which we still know is negative 1/2, gives us negative 3/2 again. So we got y, 2 instances of y equals negative 3/2, and then we got y equals negative 1, and we got y equals 3. Any questions on that? Everyone good? All right. Why don't you guys try and do this one real quickly on your own. I'll give you 2 minutes here to do this, and then we'll talk about it. All right, were you guys able to find the derivative of this, y prime?
Yes.
All right, so we had y equals u to the negative 3, right? With u equal to 1 minus 2x. So the derivative of u to the negative 3 was negative 3 u to the negative 4, or negative 3 over u to the 4th. And then times the derivative of u, which was negative 2. So our final derivative was 6 over 1 minus 2x to the 4th power. And if this represents the slope of the tangent line, well, we should be able to say that it's always positive, because what is 6? 6 is a positive number. And we're dividing it by something raised to the 4th power, which is going to be a positive number. And a positive divided by a positive is always positive. Everybody good with that? Any questions on that?
Would it be undefined at x equals 1/2?
It would be, the derivative would be, that's correct. But that's okay, because the function itself is undefined at negative 1/2, or sorry, at positive 1/2, not negative 1/2. But positive 1/2, the function itself is undefined, and so there's no tangent line at x equals 1/2, because the function doesn't exist there. But everywhere that but everywhere where it has a tangent line, it's positive. And I real quickly show you guys the graph of this function. Can you guys see the graph now?
We see it.
Yep. So the function is very, very slowly increasing. And then it actually starts increasing very rapidly as we approach that x equals 1/2 value that we were talking about. But the slopes, since this is very slowly increasing from, as it goes towards negative infinity, it's approaching a horizontal asymptote of 0. And so it's very slowly going up away from that. And the function is always increasing. Then it stops at x equals 1/2. There's no value there. And then it jumps way down here to negative infinity. And we'll note that the tangent lines are positive here, positive here. They get very, very small, but still very, very small, but positive as they go toward the horizontal asymptote to the right of y equals 0. And you might note that the slopes of the tangent line are always positive, and this function is always doing what? It's always increasing as it goes from left to right. You guys see that? Even though it jumps down here where it had that discontinuity, every point is higher than the point below or to the left of it. Does that make sense? See that it's always increasing? Yeah, no, maybe.
Yep.
All right. Okay, I think that's it for the chain rule for now. We're going to change gears a little bit, and we're going to start talking about exponential functions. So here is some seemingly random exponential function. F of x equals e to the x minus 1 all over x. I want to ask you one quick question about this function, and then we're going to move on from it. We're just going to use this result later on today, so that's the only reason we're talking about this specific one. What does it look like the limit as x approaches 0 of e to the x minus 1 over x?
Looks like 1.
Looks like 1, and I can guarantee you with certainty that it is 1. By the end of this unit, you'll be able to prove, or by the end of the time we're talking about derivatives, you'll be able to prove that this limit is 1 in about 2 seconds. So it's 1. Everybody trust me that that's 1, hopefully. It looks like 1, it is 1. So now what we want to be able to do is see if we can figure out a way to find the derivative of y equals e to the x. Hold on 1 second, and then we're going to do this. Okay, sorry about that. So if we're going to find the derivative of y equals e to the x, anybody have a good idea on how to find this derivative?
Take the limit.
All right, yeah. So we might try to think of some other ways, like using the power rule, or I don't even know what else we might think of, but none of those other ways are going to work. Power rule doesn't work because it's not x to a number, it's a number to x, so that won't work. Nothing else can end up working for this. So yeah, we're going to try a limit. We're going to do a limit as h approaches 0 of f of x plus h, which will be e to the x plus h, minus e to the x all over h. Everybody good with that? And then think about what you want to do with that. Any thoughts on what we're going to do with that? I mean, you plug in the 0 and you get 0 over 0, so it's indeterminate.
Oh, but couldn't you say that because x is or h is getting really, really close to 0, that whatever's on the top will be divided by a really small number, so it'll approach like infinity or negative infinity? Is that helpful at all?
No, because this is a very small number on the top, but this is also then a very, very small number on the bottom. So the question is, which one of these things is getting smaller more quickly, or do they get as small as each other at the same rate? So if the top is getting smaller more quickly than the bottom, then we're going towards 0. But if the bottom gets smaller more quickly, then we're going towards infinity. But if they do that at the same rate, then we should get some real number value as the limit. And there's not a good way to see which one of those would be getting smaller more quickly. So anybody see a way we can simplify this at all?
Can you distribute the h?
Distribute the h. What do you
Like
mean?
h to the negative 1 multiplied by all of them? I don't know.
Oh, I see what you're saying. Yeah, you could, but that's not really gonna do it.
Isn't there a rule where you can, like, when you subtract exponents, or like the thing when the numbers that are being raised to a certain power, can you use like a rule?
Yes, there's a rule we're going to use. Now, it sounds to me like you're saying, like, because this is e to a power minus e to a power.
Mm-hmm.
Yeah, so you're a little off. It's got to be they're being multiplied. E to something times e to something, and that's not what we've got here.
Oh, okay.
Because we got a minus between the two. But you're on the right track. We do need to use those rules because let's say, oh, somebody else got it.
Yeah,
Yeah.
Could you do e to the x times e to the h minus e to the x?
Yes, that's exactly what we're going to do. And so whoever was just talking before you, that's the idea of the rule you were using, or that you want to use, is that if we have something like, x squared times x to the third, that's equal to x to the 2 plus 3, right? It's equal to x to the 5th. And so e to the x plus h should be e to the x times e to the h. Everybody good with that? Yeah, hopefully. So how did this, rewriting the e to the x plus h as e to the x times e to the h, how did that help us out? What can we do now? What do we now have going on in the numerator here?
You can factor out the e to the x.
Right, they both have an e to the x. So e to the x times e to the h minus 1, and that's all over h. And if we plug in 0, what do we get? We still get 0 over 0. But what can we now do? What's one thing we can do with limits when I have something multiplied by something else? Shouldn't we be able to separate it into its own limits? Like that? Good or no?
Good.
All right, what's the limit as h approaches 0 of e to the x? Should be e to the x, right? Because there's no h's in there. So the limit as h approaches 0 of e to the x is just e to the x. What about the limit as h approaches 0 of e to the h minus 1 over h?
I have that in the sandwich.
1.
Why is it 1?
Because of the graph you showed us before.
Yeah, because of this thing I told you that we would use later on today. Right now, look at that. We're using it. Good. So it's the same thing. That's 1. So we got e to the x times 1, which is e to the x. So what we've gone through here and said is that the derivative of e to the x is e to the x. Does that seem right? Or
Yes.
have we made a mistake, or is that good?
That's right.
That is right. Yep. The derivative of e to the x is e to the x. It's one of only two. Well, really, there's an infinite number of functions that have themselves as their derivative, but there's two types of functions that have themselves as the derivative. E to the x is one type, like e to the x's derivative is e to the x. 2 e to the x, its derivative is 2 e to the x. The derivative of 1,000 e to the x is 1,000 e to the x. What's the other function when you take the derivative of it, you get itself?
Probably logs.
What?
Oh, probably logarithms since they're related
Oh,
to.
logs. Log. I thought you said long. I was like, long? Long? I
Oh.
don't know that function now. No, logarithm, that seems reasonable since e to the x works out that way. But it's not logarithms. Actually, logarithms become more complicated. We'll deal with those tomorrow. This is a function that we've already dealt with. In fact, it's a very, very simple, easy function.
It'd be like y equals 0. The derivative of y equals 0 is just 0.
Yep, that's it. That's the other one. So the derivative of e to the x is e to the x, and the derivative of 0 is 0. Other than that, there aren't really other functions that when you take the derivative of them, you get the function itself. So you will now memorize that the derivative of e to the x is e to the x. Yeah? And what if this was e to like a function up here, e to the u, like e to the x squared, or e to the cosine x, or e to the whatever you want it to be? Could we apply the chain rule to it, you think?
Yeah.
Yes, yes, you could, exactly. So here is the derivative of e to the x is e to the x, and then the derivative of e to a function is e to that function times the derivative of that function. That's just the chain rule expansion specifically on e to the u. Everybody good with that or no? Right, so I want you guys to see if you can do these. Take a minute or two and see if you can find the derivatives of these. Did you guys do these? Were they easy? Are you still working on them?
No.
No, not still working on them? Okay, so this was y equals e to the u, right, with u equal to x cubed plus 5x, and so our derivative is just e to the x cubed plus 5x. It's just the function we started with times the derivative of x cubed plus 5x. Easy enough? Any issues on that?
No.
All right, what about this one? This one, y prime should be just this function, e to the x squared plus sine x, times the derivative of that function, which is 2x plus cosine x. Everyone good there or no?
I'm a little confused, like, how can like for the first rule, like, derivative of e to, oh wait, no, never mind, sorry.
Okay, no problem. Any questions on that, or everybody good? All right, let's take a look at another one. Now instead of e to the x, let's try to do a to the x. So any constant down there, not just the e. So let's say 2 to the x, or 5 to the x, or 1,000 to the x power. Any thoughts on how we might go about this one?
Could we use the derivative of e to the x to help us?
We can, but first we have to get it into a form that has an e to some power. So any thoughts on how we might get it into that form?
Natural log?
All right, let's try it. Natural log of both sides gives us natural log of y equals natural log of a to the x. And is there a way to rewrite any of what's already written there? Can we rewrite natural log of a to the x as something?
Put the x in front of that natural log.
Good. Put the x in front of the natural log. That's one of the rules of logarithms, right? Then what? Any thoughts on that?
Can you make everything e to that power?
Yes, we call that exponentiating. So we'll write this
that
as
thing.
yeah, e to the natural log y equals e to the x natural log a, and e to the natural log y is just y, right? So we end up with y equals e to the x ln a. And now what do we have? We have e to a function, right? And so if we want to find the derivative of that, we can say this is y equals e to the u with u equal to x ln a. And how do we take the derivative of e to the u? It's just e to the u times the derivative of x times the natural log of a. And what's the derivative of x times the natural log of a?
what's this new one?
Well, what's natural log of A? What's A? A is just some number, right? A is 2 or 3 or 1,000. So what's the natural log of 2 or the natural log of 3 or the natural log of 1,000? It's just some number, isn't it? So I'm trying to take the derivative of some number times x. What's the derivative of a number times x?
The number.
It's just that number. So the derivative of x ln a is just ln a. So we've got y prime should be equal to e to the u, e to the x ln a, times the natural log of a. Everybody okay with that so far? Because we're not quite done. We're going to rewrite this a little bit. Any questions on how we got to there? All right. Could I rewrite e to the x ln a as something else? What does e to the x ln a equal? It equals y, doesn't it? True? Everybody agree that e to the x ln a equals y? Yeah or no?
Yes.
Okay. And so what else does y equal? It equals
E to the x.
a to the x. And so could I rewrite e to the x ln a as just a to the x? And have y prime equals a to the x times natural log of a. So the derivative of some other exponential, any value, 2 to the x or 3 to the x, is just a to the x natural log of a. And that actually works for e to the x too, because if we plugged in a equals e, right, e to the x, the derivative should be e to the x times the natural log of e. And what's the natural log of e? Natural log of e is just 1, exactly. So that would tell us that we'd have e to the x times 1 or just e to the x. So it works for that too.
Yeah, my bombs. Literally.
Everybody good with that derivative?
Yeah, makes sense.
All right. So you're going to want to memorize that one also. And you should be able to apply that to using the chain rule if it was a to some function, a to the u. So we'll do that once or twice, and then we'll be done. So if we had a to a function, its derivative is a to that function times the natural log of a, and then times the derivative of the function. So if we want the derivative of 3 to the sine x, the answer should be what? The original function, 3 to the sine x, times what? Natural log of 3 times what?
Derivative of sine x.
Derivative of sine x, which is cosine x. So the 3 pieces we're looking at here, this part here is a to the u, this part is natural log of a, and this part is du dx. Everybody good there? Any questions, any problems with that?
And it's so hard to click on these.
All right, last one we're going to do, and then we'll be done for the day. Y equals 7 to the x squared cosine 5x. So what does y prime equal? Y prime should be, this is a to the u, so the derivative should end up being a to the u times the what?
Natural log of 7.
natural log of 7, times the derivative of x squared cosine 5x. And how are we going to find the derivative of x squared cosine 5x?
Product rule.
Product rule. So we'll have x squared and then times, I still have a little room to put some coefficients in front of there, times the derivative of cosine 5x. How do we find the derivative of cosine 5x? That should be cosine u, right? Chain rule, exactly, with u equal to 5x. So what's the derivative of cosine u? That should be negative sine of u. And then the derivative of u should just be a 5. And then plus derivative of x squared, which is 2x. And then times the cosine 5x. Everybody good with that as the derivative? We see how we can put all these rules together, all these new formulas that we've got, and get a really heinous looking complicated derivative there. Any questions or any issues with what we've done? All right. There will not be an assignment that is due today. I will spare you for today. I will this evening put up an assignment that will be due tomorrow. It's going to involve chain rule plus derivatives of exponential functions. It's also going to have derivatives of inverse trig functions and logarithmic functions, which we will cover tomorrow. So that's why it won't be due until tomorrow. But I will try to get that up. I'll have it up this evening sometime. I'm not sure when, but I will get it up this evening. So no specific homework that has to be turned in tonight.